Hi, my name is Justin Mitterator, and this semester I've done research in agent-based modeling in the field of opinion dynamics. Specifically, my project was modeling polarization in mass populations using agent-based modeling in novel opinion dynamics. So first, what is agent-based modeling? So agent-based modeling is using large-scale simulations to model a population of agents. And agents, in this case, represent humans most times, but not always. And then second, what is opinion dynamics? So opinion dynamics is studying how agents interact and how influence travels throughout a population. So first, kind of just go over the agenda of the presentation. We're going to go over key vocabulary first, obviously because polarization is a pretty large topic, so we need to specify what we're specifically talking about. Next, we're going to define polarization, like I said, to define sort of the exact polarization we're talking about. Then go into quantifying polarization in terms of how are we going to get polarization down to a number. Next, we're going to see how we can add human-like behavior in the agents of our simulation, because we want the agents of our simulation to behave like humans do in real life. Next, we're going to go into the implementation of the model. So how do we actually code our simulation? Next, we're going to go into the research questions that we came up with, and the next after that, the results that we found. So first, to go into the key vocabulary, first we're going to talk about diametricity. So diametricity is if you were to think of having an opinion from on a range from 0 to 1. Diametricity is the tendency for those opinions to be closer to the poles, so closer to a 0 and closer to a 1. And this is what a lot of people talk about when they talk about polarization. Next, we have clustering. So clustering is when you have multiple different areas where agents could cluster. So for example, if you had agents with an opinion of 0.1 and then a bunch of agents with an opinion of 0.5 and then a bunch of agents with an opinion of 0.9, we would say that in that society, there's 3 clusters of opinions. And then next, we're going to talk about openness. So openness is the willingness of an agent to change their opinion. And then lastly, we're going to get into assortativity. And this is something that was very important for us this semester because it's ultimately how we measured polarization in a society. So I'll get into that more in just a second. But let's go into defining polarization. So one of our main problems we ran into was that when we were talking about polarization amongst the 4 of us who did this research, we would kind of be conflating different types of polarization. We would be saying about diametricity versus being more assorted. That in terms of having multiple types of polarization, we wanted to distinguish diametricity, which is being closer to the extremes in terms of having an opinion, and also being more assorted, which means being connected to those that are similar in opinion to you. We also recognize that polarization is not only a state, but it's also a process. So you can say that a society is polarized, and that's a state. And you could also say that they're undergoing the process of polarization. So next, we defined polarization, right, but we hadn't quantified it, and we needed to make sure that we could get it down to a number, because this is ultimately what we're going to be using as our proxy for polarization. So the way we're going to get it down to a number is calculating the numeric assortativity coefficient for each issue and then taking the average of all of those. And that'll become a little bit more clear with the next slides. So this is an example of just a graph with 8 nodes, so not too big. And this graph shows a higher assortativity because agents that are closer in opinion to each other are have a higher likelihood of being connected with agents that also have a similar opinion, right? So you have 0.9s have a higher chance of being connected to another 0.8 than they would with a 0.1 and vice versa. And this graph shows the opposite, shows low assortativities. So it's kind of more densely connected. You don't see only 0.7s and 0.8s connected to each other, and you see a 0.1 connected to a 0.6 and a 0.4 connected to a 0.8. It's just more densely connected. So after we figured out how we were going to measure polarization, we wanted to make sure that agents acted in a way that was similar to the way humans behave. So part of that was implementing some of the different parameters of the model that we ended up implementing, which you'll see in a little bit. One of those things that we found from previous research is that most times when people were simulating a society and doing opinion dynamics, they would have agents with only one opinion. And that opinion would be a 0 or a 1. And for us, we thought that it would be more similar to real society if we had agents had multiple opinions rather than just one opinion. And those opinions also existed on a continuum from 0 to 1. So you could have an opinion that was 0.5 or 0.7 and have multiple opinions on different issues. And then the last thing was that we wanted to have agents with a limited number of social connections. So in real life, we found in research that there's actually a limited number of people that can influence you. Like there is, obviously you can have access to a lot of people nowadays with social media, but there is a limit to the number of people that can influence you, which is represented as having an edge between a node and another node versus or not having an edge there. So last, we're going to get into the implementation of the model and the research questions that we had and ultimately our results. So first, how are we going to generate our graph? So basically, there's multiple different graph generation algorithms. The one that we used is Erdős-Rényi, which is what you're seeing here. This graph basically has this graph generation algorithm has two different parameters. It has the number of nodes, which is pretty obvious. It's just how big do you want the graph. Then it also has the edge probability. So what the edge probability means is what's the chance if you had any two nodes that there's an edge between those. So obviously if there's a higher edge probability, that means you're going to have more edges on the graph. And also we wanted to make sure that our graph was connected. So what that means is that if you were to take any node on the graph, you can get to any other node via some number of edges and going through the other nodes. So we didn't have any lone nodes that weren't connected to any other nodes. And we didn't have any distinct physical clusters that were separated by not having any edges. So then moving on to specifically our model. First, like I said before, for that Erdős-Rényi graph generation, we have the number of agents, and then we have the edge probability. And this is two things that I had just mentioned. So next we're gonna talk about the comparison thresholds. This was another important parameter of our model. So the comparison threshold is how we were able to gauge and change the openness of an agent. So for our model, the comparison threshold was defined as the threshold in how similar an opinion of one agent needed to be to another agent in order for persuasion to take place between those two agents. And a persuasion is basically one agent changing their opinion. So next we have the number of issues. So obviously in previous research and in the previous literature, some research has only used one issue, and we wanted to use multiple because we thought that more closely related to how real life individuals act. And then lastly, we just have max steps. So max steps is nothing too crazy. It's just a cutoff for how long we wanted the simulation to run. And this is just some noteworthy code. Our code is hundreds of lines, but this is just a short method that we wrote that actually calculates the average assortativity. So it would take the assortativity for each issue and then get the average for all the issues. So next, we're going to move into our research questions. So one research question that we had is, what effect does edge probability have on assortativity? And by assortativity, we mean polarization. And then next we had, what effect does the comparison threshold have on issue clustering? So first, we're going to go into assortativity and edge probabilities. So we found that with lower edge probabilities, you would actually have a higher assortativity. So what does that mean exactly? So basically, if you have a lower edge probability, that means that you have less social connections because the chance of there being an edge between you and other nodes is lower. We found that in cases, in the simulations where we have less social connections, you would actually have higher assortativities. And then next we had the comparison threshold and issue clustering hypothesis. So we hypothesized that lower comparison thresholds would actually result in more issue clustering, because if people were less open to changing their opinion because the comparison threshold was lower, you would actually see more clusters of issues. And this is something that we want to research more in the future, but we haven't been able to get to that yet. So we will be doing that this summer and then next fall as I continue my research. And just some more things for future research. Obviously, the first thing on our plate is to test the comparison threshold and issue clustering hypothesis. And that is our #1 priority. And then after that, we wanted to research what effect agent stubbornness has on our model. So agent stubbornness would basically be a reluctance of agents to change their opinion. We hypothesized that having agent stubbornness could lead to more polarization. And then next we could also research opinion diversion, which would be if you run into an agent that is one of your neighbors, and by neighbor, I just mean you're connected with an edge to that person. And if your opinions are far enough apart, then you can actually push each other away closer to the poles in terms of poles being a 0 or 1. And then last, we wanted to get into intelligent versus unintelligent agents. And unintelligent and intelligent agents in the sense that intelligent agents would be less likely to change their opinion and have a more nuanced opinion rather than unintelligent agents, which would just flip their opinion more easily. Thank you for listening to my presentation. You can email me for feedback or questions, or you can email Professor Davies at that email listed. Thank you.